So, have you ever stopped to think about what mathematics is actually built on? I mean, we treat it like the gold standard of certainty, right? But what if I told you that about a century ago, one single, simple question threatened to bring the whole magnificent structure of math crashing down? Seriously, this is the story of Russell's paradox, and it's all about the crisis that one little question created. And really, it all starts with this huge, kind of philosophical question. When we do math, are we discovering these eternal, unchanging truths about how the universe works? Or are we just inventing a really, really useful game with its own set of rules? You know, this is the kind of question that kept some of the greatest minds of the early 20th century up at night, especially a guy you might have heard of, the philosopher and mathematician Bertrand Russell. See, Russell was part of this movement that had this incredibly grand ambition. They were convinced they had found it, the ultimate bedrock for all of mathematics, a foundation so solid, so perfect, that it could never, ever be questioned. Their big idea was called logicism. And honestly, the sheer boldness of it is just wow. They were basically saying that math isn't some special, mysterious thing. Nope, it's just a branch of pure deductive logic. The idea was that every single mathematical concept, every single proof, could, in theory, be boiled down to and built up from only the basic rules of logic. That's it. The endgame here? To prove that math is a purely analytic science. Now, what that means is that its truths don't depend on, looking at the world or having some kind of special math intuition. Instead, they were convinced that all of math could be built from truths that were just self-evident, statements that are true just by their very definition. Okay, so how on earth were they going to pull this off? Well, their program had two big steps. First, they wanted to reduce everything to what they called formal implications. Think of these as pure logic statements that are true no matter what, not just in our world, but in any possible world you could imagine. And second, and this part is absolutely crucial, they wanted to eliminate ontology. That's a fancy way of saying they wanted to get rid of the idea that mathematical objects, like the number 5, are actual things. For them, it was all about language and logic, not objects. It's like they were building this perfect skyscraper of certainty, reaching all the way up to the heavens. And the entire foundation, the bedrock holding this massive structure up, was nothing but pure, unshakable logic. But then, a crack appeared. And we're not talking about a little surface-level thing here. This was a deep, fundamental flaw right there in the logical foundation. The whole skyscraper. It was about to come tumbling down. And here's the kicker, the truly stunning irony of it all. The person who found this fatal flaw wasn't some outside critic trying to tear it down. No, it was the project's biggest champion, Bertrand Russell himself. He was right there, working on the foundations, when he stumbled onto something that, it just didn't make any sense at all. And here it is. This is the question that nearly broke mathematics. So try to wrap your head around this. Imagine a set, a collection of things. The only rule for being in this set is that you have to be a set that does not contain itself. Simple enough, right? Okay, now for the killer question. Does this big set contain itself? This is where you fall into a perfect logical trap. Let's walk through it. Okay, option A. Let's say it does contain itself. Well, then it violates its own rule, right? Because it's only supposed to contain sets that don't contain themselves. So it can't be in there. Okay, so option B, let's say it doesn't contain itself. Well, in that case, it fits the rule perfectly. It's a set that doesn't contain itself, so it has to be in the set. You see the problem? Either way you go, you hit a brick wall, a flat-out contradiction. The logic just eats itself. All right, so right now you might be thinking, okay, that's a clever little brain teaser, but a crisis? Why does one little paradox matter for all of math? And that's a fair question. But this is where things get really, really serious. It matters because of something in logic called the principle of explosion. The old Latin phrase for it is ex falso sequitur quodlibet, which basically means from a falsehood, anything follows. And what that means is that if your logical system allows you to prove even one single contradiction, just one, then you can use it to prove literally anything. You can prove that 1 + 1 = 3. You can prove that the moon is made of green cheese. You can prove that up is down. The entire system becomes completely, utterly meaningless. That beautiful skyscraper of certainty we talked about, poof,
it turns to dust in an instant.
So the whole project was on the absolute brink of failure. And to save it, Russell couldn't just slap some plaster on the crack. No, he had to pull off an incredibly ingenious escape. And he did it by completely redefining one of the most basic ideas in all of mathematics. Here's the key. The whole problem, the paradox, it came from thinking of a set or a class as a real thing, like a physical box that you can put other boxes inside of. Russell's solution, which he called the no classes theory, was to say, wait a minute, that whole idea is just wrong. A class isn't a real object. It's just a piece of linguistic shorthand. It's a way of talking about a property, like the property of being a teacup. It's a description, not a container.
Yeah, in his own words, he said, symbols for classes are just incomplete symbols. Basically, they're convenient labels we use, but they're not names for actual things that exist out there in the world. He pretty much solved the paradox by declaring that the thing causing all the trouble, that set of all sets, was never a real thing to begin with. It was just a phantom, a ghost created by a clumsy use of language.
And that was the genius of it. By changing the rules of the game, by redefining what a class even is, the question that caused the whole mess, that self-referential nightmare, couldn't even be asked anymore. It became logically impossible to even form the sentence. You can't ask if a piece of shorthand contains itself. The question just becomes nonsense. So the paradox wasn't really solved in the traditional sense. It was dissolved.
And that just leaves us with this one final fascinating thought. This whole roller coaster started with a search for absolute, unshakable certainty by grounding math in pure logic. But the search itself showed that even pure logic can hide these devastating paradoxes deep inside. It kind of proves that our foundations of knowledge might be a little more fragile, a little more dependent on these clever definitions than we might like to admit. And it really makes you wonder, if we can't find ultimate certainty in pure logic, where can we find it?